So today is our review day for exam 2. I think it'd be good to start by reviewing more basic things about hypothesis testing, confidence intervals, reminding you of method of moments and maximum likelihood, and some of the theory with regard to bias and consistent estimators and that kind of thing. And then we'll save some other stuff for later. Maybe the very last thing would be the harder stuff regarding, for example, convolution and Neyman-Pearson. Maybe in between, we can talk about chi-squared a little bit more. Should be able to do that. I haven't emphasized p-values in this class, but you should certainly be able to compute p-values. Let's start with an example like that. It's certainly simplest to talk about hypothesis testing, ideas, including type 1 and type 2 errors, power of a test, and p-value, I think, in the context of, say, testing a mean, where you are assuming you know the population variance, in other words, the population standard deviation. So let's assume we've got a situation where we are testing a null hypothesis that a population mean equals, say, to make up a number, 20. I won't specify an application. And the alternative, let's just go ahead and make it left-tailed to be different here. Mu is less than 20. I will also mention what to do if I decided to make this two-tailed, make it a not equal to. Though I'll write the hypothesis test as a left-tailed test. Let's approach doing the test in two ways, both the classical way where you're talking about rejection regions, again, also called critical regions, specifying alpha, and also let's do it with the p-value approach. All right, so let's say our sample size is known to be 25. Let's say the population variance. It's hard to know exactly how big to make this to make things work out nicely, but let's just pretend it's 16. Of course, that will make the population standard deviation equal to 4. If we decide on an alpha ahead of time, let's make it be smaller than usual this time. Let's make it be 1%. That can help us figure out our critical region in terms of z pretty easily. So we're looking for the critical region of a left-tailed test. This is supposed to be the standard normal distribution, N01. If it's a left-tailed test, then I want a critical region that's to the left of some number that could be verified with Neyman-Pearson that would be a best critical region, most leading to a most powerful test for the given level of significance. And it'd actually be after, symbolically, you'd call it z sub 0.99, right? If I want the area to the left of that to be alpha 0.01, then technically that's z sub 0.99. The area to the right of it would be 0.99. However, of course, by symmetry, this is the opposite of z sub 0.01. Let's use the calculator. Of course, on the calculator, I don't have to think of it that way either. I could just go to my distribution menu, go to inv norm. This is giving CDF values. So z sub 0.99, the area to the right is 0.99, but the area to the left is 0.01. So I can just put a 0.01 in there. What should this be? -2 something, right? That's what this should be. -2.326. So your critical region, you would reject the null if your observed z statistic value is less than or equal to -2.326. And that's going to be a test where alpha, the level of significance, the probability of a type 1 error, is going to be 0.01. Still not quite thinking about the p-value yet. before we think about the p-value, let's think about other things. Let's think about, for example, the power of the test. I could ask that kind of question. What is the power of the test and the probability of a type 2 error against a specific alternative? Well, maybe against is the wrong word. When mu takes on a certain alternative value, what should I pick? I'm trying to guess what might be a reasonable thing to pick here. 18. What is the power when mu equals 18? If I'm going to figure that out, I really do need to figure out what the rejection region is in terms of X bar. On a test, maybe I'd tell you just to save some time and also save some mistakes. But just in real life, if you're going to figure this out, you've got to figure out how does this rejection region correspond to a value of X bar. I think I got to think about standardizing X bar if the null is true. The null value, mu sub 0, is 20. So I'd want to subtract 20 and divide by the standard deviation of the sampling distribution of X bar. By the way, it's sometimes called the standard error of X bar. I haven't really emphasized that. Sigma over square root of n is going to be 4 over square root of 25. I've got to figure out, solve this inequality for X bar. What's the corresponding simple inequality in terms of X bar? It's X bar less than or equal to something smaller than 20. What is it? Well, that's 5, making this a 4/5. Multiply both sides by 4/5. .8. You get negative 1.86108. Add 20 to both sides. The equivalent inequality, simplified inequality in terms of X bar, is X bar is less than or equal to 18.14139, let's say. That's the rejection region in terms of X bar. Why is that important to find? Remember what the power is. The power is the probability of correctly rejecting the null when the alternative is true. Think in terms of a prosecuting attorney. A prosecuting attorney wants lots of power. They want to be able to reject the assumption of innocence. They want to be able to convict if the defendant truly is guilty. They want to have a high chance of doing that. Of course, they might be corrupt and want to convict them if the defendant is even innocent. But for sure, if the defendant truly is guilty, they want to be able to convict. They want high power to do that. The power is going to be the probability that, write it in terms of X bar, that I'm in the rejection region, assuming the assuming the alternative is true. What alternative should I pick? It's the one I told you to pick. In real life, which one do you pick? Pick the alternative value that's sort of the minimal alternative value that you'd like to be able to detect with high power. You know, if it's important to you to be able to detect when mu is 18, then pick mu to be 18. If it's important for you to be able to detect mu is 18 or smaller. If it's not so important to be able to detect when mu is 19, yeah, then pick something smaller like 18. In real life, you have to think about those practical kinds of considerations. Standardize, convert to Z. So now we subtract 18 instead of subtracting 20. but we still divide by 4/5. And this power is not going to be real high, but it will be slightly bigger than 0.5 at least. .139 divided by 0.8. Let's say 0.174. A little higher than 0.5 is what it's going to be. Use your calculator. Normal CDF. 0.174. A little higher than 0.5. About 0.569 is the power. Ideally, most people say you want power at least to be 0.8 or higher. So how do you fix this? Well, you either adjust your target, make mu smaller than 18, like 17. That'll give you a bigger power because this number will be bigger. Or if you really want to detect when mu is 18, pick a bigger sample size. Make the sampling distribution skinnier. Beta, the probability of type 2 error is the 1 minus the power. That's going to be about 0.431 then. All right, what about the p-value approach? You've read about this, and we certainly learned about it in Prob and Stats, but I haven't emphasized it in this class because we've been focused on the classical approach for the purpose of looking at the Neyman-Pearson Lemma mostly, because you got to think about it in terms of the classical approach with the Neyman-Pearson Lemma. P-value is always the probability of observing a test statistic as extreme or more extreme than what you actually observe when the null is true. That's a mouthful, but it's worth writing down. Probability of observing a test statistic, and you should know this for the exam, maybe even a multiple choice question, as extreme or more extreme as what you actually observed, under the assumption that the null hypothesis is true. That's always what the p-value is. In any situation. Of course, that means you got to know a test statistic. A relevant test statistic. And then the logic of thinking about making a decision with p-values is this. This is really key as well. Maybe I'll ask you a multiple choice question about what I'm about to say. The logic is this. If the p-value is small, really small, how small is really small? It is a matter of opinion, but again, our standard is of 5% that most people sort of default to. Is that really the best thing to default to? Not necessarily. It's just sort of habit, tradition. If the p-value is really small, then you have observed something rare when the null is true. Therefore, we think the null is false. Don't ever think that the p-value is the probability that the null is true. That's sort of the common misperception. Oh, the p-value is the probability that the null is true. It's small, therefore we think the null is false. No, that's not what it is. Nobody can figure out the probability that the null is true. Nobody can do such a thing. It's impossible. Not even a well-defined question, probably. I mean, when you think about it practically, I mean, if you're thinking about two-tailed tests, the probability that the null is true, even though it can't really be found in in any ordinary sense, you might say is 0. If it's a two-tailed test, right? The probability that mu equals 20 exactly, there's pretty much no chance. But that's not the philosophy of hypothesis testing. The philosophy is you give the null the benefit of the doubt until proven otherwise, so to speak. These are important issues. And it's important to, help your future work colleagues to understand that. And they do have practical ramifications in terms of misunderstanding statistics and stuff. People use up p-values all the time, but they really don't understand them. It's the probability of observing a test statistic, like a z statistic or a t, as extreme or more extreme than what you actually observed, greater than or equal to or less than or equal to, under the assumption that the null is true. So when it's small, you observe something rare if the null is true. Therefore, you think the null is false.
How is this different than alpha?
Alpha is the probability of a type 1 error, the probability of incorrectly rejecting the null if you assume the null is true. It's when the p-value is less than alpha, when you get a p-value and it happens to be less than alpha, that you say, okay, I'm going to reject the null, and therefore my probability of a type 1 error is alpha. I'll say that again. Well, let's just go ahead and compute it for an example. Let's go ahead and suppose we get an X bar that I know ahead of time is going to be in the rejection region in terms of X bar. Let's pretend we get X bar equal to 18.1, say. Suppose the observed value of X bar is 18.1. The p-value of the test then is the probability of getting X bar less than or equal to 18.1, given that the null is true. I mean, usually when we compute a p-value, we don't write it in terms of X bar. We usually pretty much just compute z first. Assuming the null is true, so subtract 20. So we have negative 1.9 divided by 0.8. The observed value of the z statistic is negative 2.375. So usually I don't write that first line that I just wrote right here. But it's not a problem to write that. And it is a less than or equal to here because it's a left-tailed test. Less than or equal to is what it means to say as extreme or more extreme. It's always with regard to the direction of the alternative hypothesis. With a left-tailed test, we want a less than or equal to. But by what I've just computed here, that's the same as the probability that z is less than or equal to negative 2.375. And by what I've done already, that's going to be a little less than 0.01. Negative 2.375. I'm going to get something slightly less than 0.01. 0.009. So the p-value is 0.009, less than alpha, slightly less than alpha. To decide to reject the null, you don't have to think about alpha. You could just say, hey, I got a small p-value. I've observed something rare when the null is true. Therefore, I reject the null. You don't have to think about alpha. However, in the classical approach, you do decide alpha ahead of time. You do decide the rejection region. You could reject the null just looking at the z statistic and seeing, oh, it's in the rejection region. And you don't have to figure out the p-value. The more new approach is to figure out the p-value to specify exactly what the probability of observing the test statistic is if the null is true, as extreme or more extreme. If you want to relate it to the classical approach, then you say, oh, it's less than alpha, so I reject. This is equivalent to z being in the rejection region. Because it's less than alpha, you are rejecting the null. Therefore, your type 1 probability of a type 1 error is alpha. Though we get into subtleties there too, because technically speaking, you've already done your random sampling. So again, probabilities are really best interpreted before the fact. If you decide what alpha is going to be, 0.01, it's best thought of as a probability before you actually do your sampling. You've set things up, you've got a sample size of 25 and a standard deviation of 4. With this hypothesis test, I'm about to do the test. What are the chances that I'm going to make a type 1 error? That's what the best interpretation of the 0.01 is. I happen to get a p-value smaller than that, so I do reject. Saying that my probability of a type 1 error now is 0.01 is an after the fact probability. Is not quite technically the best interpretation of probability, but most people don't worry about it. But don't ever say the p-value is the probability that the null's true. It's not. There's no way anybody can find that. Maybe instead of emphasizing that the null is mu equals 20 exactly, maybe you start emphasizing that the null is mu is 20 with maybe a little bit of cushion, a margin of error or something, but I'm not going to get into that either. We want to keep things simple. I mention these things to you so that you just realize maybe you've had misperceptions about things and plenty of other people do too. Sometimes the technically bad way of thinking about it doesn't have any effects. Like, oh, to think of this as a probability of a type 1 error now after the fact, it's not a big deal really. But it is an after the fact probability, which is technically not correct. It's kind of like with confidence levels with confidence intervals as well. If this had been a two-tailed test, mu not equal to 20 in the alternative hypothesis, I'm telling you, you should be able to handle it. As far as the p-value goes, you just double it. Just double the one-tailed p-value. As far as the rejection regions, it's actually a bit trickier. Right, I'd have to find two tails for a two-tailed test where the area of both of them add to 0.01. So the area of both of them would be half of that, 0.005. So p-value approach, just double the one-tailed p-value for these symmetric distributions, at least. With the rejection region approach, it's a bit trickier. You got to split your rejection region into two pieces. I haven't really talked about t-distributions in here because we've been focused on other things, but you should be able to handle the case where sigma is unknown and you have to compute S, and you got to use a t-distribution with n-1 degrees of freedom for means. It gets extra tricky as far as computing power and stuff, so probably I would not put that on the take-home at least, or on the in-class at least, and probably not on the take-home either because it hasn't been an emphasis, but you should certainly be able to do a test and decide whether to reject the null or not. Compute a p-value using a t-statistic, using S sample standard deviation. I think I have a sense of homework problems like that. And confidence intervals too. Again, how is this related to Neyman-Pearson? Neyman-Pearson in this kind of context is just confirming what seems the most obvious natural thing to do. With a left-tailed test, the rejection region is everything to the left of something is the best kind of critical region. Not something weird, like maybe you pick a Z where this area is 0.005, and maybe you pick some other region in here where that area is also 0.005 and use that as your rejection region. That seems silly. Neyman-Pearson just emphasizes, yes, that is silly. In this kind of context, don't do that kind of thing. It's not as powerful. And it's, from a logical standpoint, it just doesn't make any sense. But we did see there are some examples with Neyman-Pearson where unexpected things do happen. Maybe your test statistic is even the product of random variables instead of the sum or a mean. Let's talk about chi-squared tests a little bit more now as the next thing to do today. So I introduced that last Thursday. The example that we focused on last Thursday was my basketball shooting. Trying to wonder whether if I ran an experiment of doing 5 free throws at a time, counting the number that I make, I either make 0, 1, 2, 3, 4, or all 5. And then doing that experiment, I think it was 200 times for 1,000 total free throws, but 200 experiments of 5 free throws at a time, and seeing if the observed data matches the expected data, if I really do have a binomial distribution with 5 when I do 5 free throws with n equal to 5 and p equal to 0.4. But chi-square test is broader than that. You can use it to test, for example, any set of proportions that add up to 1. For example, what's your favorite kind of pizza? All right, I'm not going to list every kind of pizza here. There's our classics here: pepperoni, sausage. Okay, I could do sausage and mushroom. I could do, whatever. There's Hawaiian. My son hates Hawaiian. He's like, why would you put pineapple on a pizza? I like it. We always used to call it Canadian bacon and pineapple, but now we call it Hawaiian. And one more, the works. 5 meat or whatever. Veggie, whatever. Okay. So you got 4 kinds of pizzas there. Pizza type. And we could have null hypothesis values for what you think the favorite picks are. Null values for favorites. Your hypothesized null values. Maybe you think pepperoni is definitely preferred by maybe not a majority of people, but a plurality. You know the difference between a majority and a plurality? Majority is what? Greater than 50%. Plurality is not necessarily greater than 50%, but the highest percentage is a plurality. Should not go out of a stats class, technically speaking, without knowing that. Let's say pepperoni is not a majority, but a plurality. You think 40% of the people, their favorite pizza is pepperoni. And all the other ones are going to be smaller. Sausage, you think it's 0.3. Hawaiian, you think it's okay. I guess I'm going to go down one by one here. Is 0.2 and 5 meat is 0.1. So those are your null values for the favorites. How many people are we going to survey their favorites, and they can only pick from these 4? Let's say we survey 1,000 people at random, and it's 1,000. Oh, let's make it 100. So survey 100 people at random. What's your favorite from these 4? We'll get some observed values. We can also compute expected values. You could call them EI equals N times PI, as the book does in chapter 15. Assuming N is 100, multiplied by these proportions, 100 times 0.4 is 40. 100 times 0.3 is 30, 100 times 0.2 is 20, 100 times 0.1 is 10. What are the observed values? Call them OI. Make your O cursive so you don't think it's a 0. Because of randomness, even if these are the true proportions, true population proportions, you're not going to get exactly these numbers. Let's try to make them far enough away from the expected values that hopefully we end up rejecting the null. Let's make this one be 30, say this one be 33. This one, to please my son, let's make way down at 5. And then these do have to add up to 100, so that's going to leave, what am I up to, 68 there? It's going to leave 32 for that one. Wow. So those look far enough away from the expected values that I'm sort of thinking we're probably going to reject the null, because what is the philosophy of hypothesis testing? You're assuming the null is true. You're giving it the benefit of the doubt until, quote unquote, proven otherwise, until you have strong enough evidence to suggest you think the null is not true. Getting a p-value that's real small. Observing a test statistic that gives you a p-value very small, meaning you have observed something rare if the null is true. Probably getting some sort of large test statistic. Although, what is the direction of the alternative hypothesis here? Does it have a direction? The null really is that P1 is 0.4, P2 is 0.3, P3 is 0.2, and P4 is 0.1. And what's the alternative? The alternative is just the opposite of the null, meaning at least one of those P's is not as specified. You could just write not the null. At least one PI is not as specified. Although if one of them is not as specified, then at least another one would also be not as specified, right? Because they have to add to 1. Again, intuitively, the chances the null is true is essentially 0, right? That these numbers are exactly right. It's probably even really close to 0 if you gave yourself some cushion with each one of them. Be very unlikely to for all this to be true, even with a little bit of cushion. Though technically speaking, nobody can really figure out that probably, because nobody knows the population well enough. And only God knows if it's true or not. And with regard to truth, it's probably not true. But we give the null the benefit of the doubt. That's the purpose of hypothesis testing. You don't reject it until you got strong enough evidence against it. So we need a test statistic. And what chapter 15 gets into is the test statistic happens to have a chi-square distribution. So we call it a chi-square test statistic. Chi-square test statistic. That's not an X, that's a chi. Chi-square. Summation I goes from 1 to not n. This is a little tricky with the notation. N is the sample size of the number of people we're surveying. 100 people. But we don't have 100 categories of pizza. We only have 4. Book calls it K for the number of categories or bins. This is categorical data that we've got about pizza preferences. Observed minus expected squared divided by expected is the way you compute it. With how many degrees of freedom, not n minus 1, but k minus 1. So in this case, that's 3. K equals 4 for us. 4 categories of pizza. I could have added more pizzas, and so K would be bigger, but that's the way I chose to do it. Technically speaking, calling this a chi-square random variable is actually only an approximation. And the approximation becomes better and better under certain conditions related to how big these numbers are actually. So we got to compute, we could extend the table and compute. Now let's just go ahead and compute these fractions straight away here. OI minus EI squared divided by EI. So here we've got 30 minus 40 squared divided by 40. So that'll be 100 over 40. Now what's that, 2.5? Relatively extreme, relatively large value there. This next one's going to be smaller. 33 minus 30 squared over 30. That'll be 9 over 30, which is 3/10, 0.3. This next one's going to be fairly big. 5 minus 20 squared over 20. 15 squared is 225 divided by 20. Going to get something over 10 here. It's going to be an extreme one. 11.25. And then this one's going to be extreme as well. 32 minus 10 squared over 10. 22 squared over 10 will be 48.4. So yeah, the sum of these things is going to be pretty big. We're going to get a pretty extreme observed value of chi-squared. At least it seems that way. Then now the number of degrees of freedom is certainly going to affect the p-value. 62.45 is the observed value of chi-squared for these data. What is the p-value? The p-value is the probability of observing a test statistic as extreme or more extreme. In this case, that means chi-squared greater than or equal to 62.45, assuming the null is true, which you don't have to write in the notation. I'm implicitly assuming the null is true by computing these expected values as part of the calculation. And how many degrees of freedom is it? It's 3 degrees of freedom. So you could put a subscript of a 3 there. That subscript means the degrees of freedom. It does not mean an area to the right of something. Could use the table. We can also use the calculator here. It's a chi-squared CDF. So I'd have to, whatever I get, I have to do 1 minus it. Or I guess I could do a different lower and upper. I could do a lower of 62.45 and an upper of essentially infinity. Let's do it this way. What should I expect here? This is a CDF value with a high upper. This should be a fairly large number, close to 1. It says it is 1. Does it equal 1 exactly? No. Is it carrying more decimal places internally? I don't know. Doesn't look like it. The p-value is essentially 0. I wonder if we did the other way, if we get something with like, that would be like 10 to the negative 30 or something. I don't know. Let's see. Does it? I'm not using the E there. Will this work? Okay. About 1.76 times 10 to the negative 13. Which probably best to write as approximately 2 times 10 to the negative 13. 10 to the 12th, 10 to the positive 12 is a trillion, right? Yep. This is like 1/10 trillionth of a chance of observing something this extreme or more extreme if we assume the null's true. Therefore, we are very confident the null's false. We reject it. Is it possible to do the classical approach instead of the p-value approach? Yeah. If we were doing the classical approach with deciding what alpha is ahead of time, say 0.05, so I'm not sure if the calculator has an inverse chi-square. Nope, doesn't look like it does. You'd have to, well, you could use the table. You could do some guessing. Let's use the table to help us do some guessing. Chi-squared table is what I'm looking for. 3 degrees of freedom. Well, and the table gives us a good enough answer. 3 degrees of freedom. These numbers up here, you can see by the shading, are CDF values, areas to the left. We want the area to the right to be 0.05, so the area to the left has got to be 0.95. 3 degrees of freedom, our critical value is 7.81. The rejection region is when chi-squared is greater than or equal to 7.81. When alpha is 0.05. And then you could test it with the calculator if you wanted to. So this should give 0.95. Yeah. Okay. So yes, you can do it in terms of rejection region without figuring out a p-value, but you should feel comfortable either way. Would I put this in the in-class exam? Possibly, yeah. It's straightforward enough that we could probably do that. Okay, so that's something you should be able to do for the in-class exam. I'm going to share I'm not going to go through into details here, but I'm going to share a PowerPoint with you. That shows you can also use chi-square test to test a null hypothesis that a random variable takes on a certain continuous distribution. This is the PowerPoint I'll share with you, where I did a few different simulations with a spreadsheet using, I'm not going to test you on this, using equals norm inv and rand 400 times. What I was trying to do was test to see if the spreadsheet is working correctly, effectively. Is that spreadsheet code truly going to generate simulated data from a standard normal distribution? Rand, remember, is supposed to generate numbers from a uniform distribution on 0, 1. And then if I plug them into norm in with a mean of 0 and a standard deviation of 1, this is an inverse normal, that should give me corresponding normal z values. And the null hypothesis is that the distribution is normal with variance 1, standard deviation of 1. And the alternative would be the opposite of that it's not. It's a continuous distribution. I'm not testing pizza preferences here. I'm not testing proportions. I'm testing whether something follows a certain continuous distribution. And the normal is the most common thing to use here. You still want to make a chart effectively, separate the data into categorical bins and count. You have expected frequencies and observed frequencies. My initial thought was to try it with bins that were, well, not all the same length, but many of them are the same length of 0.5. However, that leads to p-values, proportions, probabilities that are not the same. And the bin counts are therefore not the same. Anyway, you can do it, and I did, and you get a chi-squared value. There are 10 bins here, so there's 9 degrees of freedom. Get a chi-squared value there, and the p-value is not very small, so don't reject the null. And this would be a situation where you're kind of hoping you don't reject the null. You're hoping the spreadsheet's working fine. Turns out bins of equal length is not the best thing to do. It's best to use bins of equal probability effectively. All these bins, these intervals, represent under a standard normal curve regions of approximately equal probability equal to 0.1. A little more precisely, this is what they are. And therefore, these expected bin counts are all approximately 40. When the sample size was 400. And you get different bins and you get different expected counts. And that test turned out to have a high p-value as well. Don't reject the null. So the spreadsheet, as far as we can tell, seems to be working fine. Okay, so just showing you can do it for continuous distributions. If you have to, I was assuming the mean was 0 and the standard deviation was 1 here, and I was assuming those were right. If it's not coming from a spreadsheet where you're assuming those kinds of things are right, and you have to estimate the mean and standard deviation with the data actually, then the degrees of freedom, it turns out to not be k minus 1. It turns out to be k minus the number of parameters that you're estimating minus 1. So you get a smaller number of degrees of freedom. And when you get a smaller number of degrees of freedom, it makes it harder to reject the null. The p-value ends up being bigger when the degrees of freedom is smaller. I'm not a statistician, but I did talk to a statistician about this. And he said that, yeah, people sometimes do this, but it's actually not the best thing to do. It's not really widely used because it's got low power. The power of the test can be low. And so people typically use other things when they're trying to test for normality. Just a little side note, I'm not going to test you on it. I'll share this PowerPoint with you if you're interested. All right, with our 18 remaining minutes, let's review the harder things as much as we can. Maybe working backwards with Neyman-Pearson, the most recent thing. Just emphasizing the main ideas. Details of examples, of course, would be what comes up on the test, though I suppose in the in-class portion, I could still test you on true, false, multiple choice kinds of things with these. Then we'll work backwards, ultimately getting back to like convolution. The time we have. I'm just trying to emphasize the main ideas here, remind you of them. So with Neyman-Pearson Lemma, most of the examples we did were like this. We did have one example last Thursday, and you had a homework problem that was not quite like this. Most of the time, we're comparing two simple hypotheses. A null hypothesis that theta, a parameter, equals theta sub 0 versus an alternative that theta equals theta sub 1. And you would want those to be different, otherwise you wouldn't do the test. Most of the examples, if not all of them, for us, theta 1 was bigger than theta 0 is effectively a right-tailed test. The Neyman-Pearson lemma is saying effectively that rejection regions that satisfy this kind of inequality are the best ones, where that is the likelihood ratio. L of theta is the product of the PDF values in the continuous case. You could call them PMF values in the discrete case. Right, it's this thing that we also use for the method of maximum likelihood estimators, which you should also review. With that, you're trying to think of the x's as fixed and think of it as a function of theta that you're trying to maximize as a function of theta. Often easier to take the natural log and maximize that. But here we're just saying, okay, it's a likelihood thing. And actually, when you're thinking about the Neyman-Pearson lemma, you change your perspective and typically think of the theta as fixed and the x's as, well, you could call them variables. Are we truly letting them vary? Or it's more that this inequality defines a set of values of x that defines the best kind of rejection region. And we saw many, maybe many is not the right word. We saw some examples of this. One example that we saw is related to the hypothesis test we did 30 minutes ago, testing a mean. So theta is mu. When the population distribution was normal, the x's were normal. And the likelihood function involved, it was kind of complicated, 1 over square root of 2 pi, sigma, and e is something. And we had to compute the likelihood ratio. Some things canceled. We could simplify it. We just said, okay, this thing that we're looking at when we compute the likelihood ratio is less than or equal to k. That the inequality defines a best critical region, rejection region, in the sense that it makes the power of the test as high as possible for the given alpha. The value, the little k, depends on what alpha is. I'm giving you homework problems for finding little k. We also saw that you typically try to simplify the inequality. In the case of testing a mean with the normal distribution, we simplified it in terms of the sum of the xi's and ultimately divided by n to relate it to the mean, x bar, being for a right-tailed test greater than or equal to some number we call typically big K. Am I going to test you on doing the algebra? I'm not ruling it out for the take-home, I guess. More typically, I did the algebra for you in class, and I just had you use the results, either to solve for little k or to find big K when you know alpha. And then you could also find the corresponding little k. Really, actually finding the corresponding little k is not the main point. The main point is to look at the simplified thing with the big K. Remember all this? And you got to use the distribution. If you're using X bar, when you're dealing with normal, you can convert to Z. You can use a Z statistic distribution to figure out what the rejection region should be based on a given alpha. You can figure out the power and the probability of a type 2 error. It's easy actually for simple hypotheses with power and type 2 error because your alternative hypothesis is not a greater than or a less than, it's an equal to still. Then there were a few weird examples. Sometimes had to deal with gamma distribution, I think, chi-squared, in some of the examples that we looked at in class and I had you do homework problems about. Sometimes have to use Mathematica to do the calculation for you. Calculator might come in handy, but I think we mostly focused on using Mathematica to relate it to the other ideas about hypothesis testing, alpha, beta, power. The last example we did Thursday, and I had a homework problem. These hypotheses were hypotheses about the PDF of some random variable. There's a discrete case that we did in class. You did homework with a continuous case. This is just saying alpha is the probability of a type 1 error, probability of being in the rejection region when the null is true, and it does equal that integral, but you don't have to worry about doing the integral. Well, I mean, I guess there's some cases where you have to do an integral. Sorry about that. But we would never do a case where you'd have to do an n-tuple integral, right? It would always be n is 1 or 2 to keep it simple. So I guess you do have to think about this in those cases. Continuing to go backwards. We also had content about estimators. Yes, method of moments and maximum likelihood. But we had that, it was class 13 where we had all those definitions and facts. So you should definitely review this and put some things on the note card. Do you have to put all these PMFs and PDFs on the note card? No. You can use the table. I mean, the T distribution and F distribution PDFs are not in our tables. They are, the T distribution one is in the book in a certain spot, though it actually doesn't look like this. It's equivalent, but it doesn't look like this in our book. It's more that you should know the definitions and the examples that are mentioned, or be able to verify the examples. What is an estimator? It is a statistic, which means it's a random variable that is a function of a random sample. Random sample automatically assumes the variables are independent. Here's the notation for it. Theta hat is your statistic. The U is just a function name. It's common to use U in this context. In the case of a sample mean, the U is this function of the xi's. This is a statistic. It's a random variable. It's got a distribution. Knowing the distribution helps you do inference, helps you do confidence intervals and hypothesis testing. And the mean of X bar is the mean of the population. This X bar is a natural estimator for mu. It also ends up being unbiased. It's not said here, but said further down. It's unbiased. The mean of the mean is the mean. Expected value of X bar is the expected value of X, mu. We said this is kind of silly, but it's something you could do. There's nobody stopping you from doing that if you wanted to. Taking X bar and adding 1 over n, though you might get fired for doing it on the job. But for the purposes of theoretical math and trying to understand ideas, it's an estimator you could use for mu. It's not unbiased, though it was asymptotically unbiased as n goes to infinity. Of course, there's knowledge here. You should know the sample variance where you divide by n minus 1 is an unbiased estimator for the population variance. Though the sample standard deviation is not an unbiased estimator for the population variance. You had a homework problem about that. Verifying that. If we decided to divide by n instead of n minus 1, our book calls that in a couple spots sigma squared hat. This other book that I have calls it t squared, but it's not a t distribution. Divide by n instead of n minus 1 is not unbiased. You could call it biased. X bar over n is a natural and it turns out an unbiased estimator for the probability of success for a binomial random variable. These were statistics that we got from a gamma distribution as from the method of moments. I suppose another possible third problem on the take-home could be using Mathematica to do simulations, or maybe I'd weave that into the first 2 problems in some way. Should be able to use random variate. Probability distribution was another command, and compute means and variances and so forth. Then we had our other main example was related to right endpoints of uniform distributions. You should know these facts. 2 times X bar is an estimator for the right endpoint. You could call it natural. I'm not calling it unbiased here, though it is unbiased. The maximum of the data is also a natural estimator for the right endpoint of a uniform, though that turns out to be biased. However, if you multiply it by n plus 1 over n, then it's unbiased. It's a different estimator than 2x bar. They're both unbiased, but they are different from each other. And in general, they give different values. They're computed differently. For a given random sample, they will equal different things. But as theoretical estimators, they're both unbiased. They both have a mean equal to the right endpoint, the unknown parameter. The bias of an estimator is its expected value minus the parameter value. If you assume you know what the parameter value is, you can compute this. And theta hat then is unbiased if the bias is 0. Yep, there's where I say 2x bar is unbiased. It's a fact to know for the test, including the in-class. You can put it on your note card, it's fine. This again is not unbiased, but this one is unbiased, like I just mentioned a minute ago. Asymptotically unbiased estimators just has a bias that goes to 0 as n goes to infinity. Like this one. In other words, if the sample size is large, it's probably pretty good anyway, even if it's not unbiased. Consistent estimators. Okay, this is a real technical definition. I'm not going to test you on this technical definition. But you should know this theorem. Got a random sample from a population, and theta hat we already know is unbiased. If the limit of the variance of theta hat goes to 0, then theta hat's going to be consistent. Not only is it unbiased so that its observed values don't tend to systematically over or underestimate theta, it also has small variance for large sample size and therefore also small standard deviation for large sample size. The sampling distribution is going to be skinny. So you can say the observed value theta hat is going to be good when n is large. Relative efficiency, we only spent one day on that. Essentially, theta 1 hat's relatively more efficient than theta 2 hat if the ratio of the variances go to 0, or that is the relative efficiency. And if that's small, then you say, theta 1 hat's a lot better, more efficient than theta 2 hat is for a given sample size n. I did do an example calculating the relative efficiency of theta 1 hat and theta 2 hat for the right endpoint of a uniform here. And I think I did give one homework problem about that. So maybe true, false, multiple choice questions for the in-class, and maybe it could be related to a third take-home. I don't know. We didn't spend a ton of time with it. 2 minutes, convolution and sums of random variables, either double integrals or single integrals with convolution. Of course, we can't do this justice in 2 minutes, of course. I've given you a lot of problems related to it, though. You got a lot of practice. You might have forgotten it already. We've done lots of situations where we added 2 independent random variables and we did double integrals to figure out with the CDF method to figure out the CDF and then differentiate to find the PDF. Though you have to think about cases, and that's the trickiest part. We even did one example where the variables were not independent. But to do such an example, you do have to have the formula for the joint PDF. And then there's convolution. Yeah, on the take home, I'm going to give you the option. This was the derivation of the convolution formula. Essentially, this integral on the right here, this single integral, gives you the PDF of x plus y when x and y are independent. You only use the convolution formula when x and y are independent. If they're not independent, if they're dependent, you've got to use a double integral. But I'm going to give you a problem on the take home. That's the first problem I'm writing, where I'll give you the option. You can either do it by double integral or you can use the convolution formula. I imagine probably most people will do a double integral because it just feels easier. But for practice, you could also try it with a convolution. You will have to think about cases again. And that's the trickiest part. So it's an odd mixture of, in exam 2 here, a mixture of things you already know and new things. But it seemed like the best thing to do to me in this time since spring break. Again, after the exam starting on Tuesday, we'll get into R and also regression, both simple regression and multiple regression. All right, I'll work on getting that take home to you as soon as I can.